Good day, Doctor. We are from Group Last Minute, and this video is to present our RTSE assessment tool. And the title is a concurrent UCOS2 style real-time control system for the speed trial 2D autonomous driving simulation. And I'm Tam Jia Hao. My teammate is Paul Zing, Quan Qitong, and also Tan Yuchu. So for the agenda, we will start from the introduction problem statement, background, RTOS concurrent design, decision logic inside the analyzed drive functions, case study and comparative benchmarking, followed by the key findings, redesign, real-world validation, and also the conclusion. So let's start from the introduction and background. For the introduction and problem statement, in the real-time system, the correctness depends not only on the producing the correct result but also on producing it at the correct time. For example, if an obstacle is detected after the vehicle has already passed it, the system has failed even though the detection was correct. So the goal of this project is to develop a concurrent controller for speed trials 2D and use this as a basic for the future physical real-time system design. So there are three main challenges. First one is the concurrency. The serial design causes the vehicle control wait for the slowest vision frame, increasing the latency. So the second is timing determinants. The task must execute at the correct intervals to prevent steering delay and unstable behavior. Third is safe resource sharing. The camera frame and control command must be shared safely between tasks without a race condition or blocking delay. So for the time critical event, the simulation contains several time critical events including the low light conditions, chasing car, police car, speed modifying tokens, and golden light that require the lane number recognition. Each event reduces the available reaction time and tests the controller responsiveness. So for the background, concurrency, and the simulations, to address these challenges, the system must use the concurrency, where the multiple tasks operate simultaneously, unlike the sequential execution, where total response time is the sum of all processing steps. Concurrent execution reduces the response time by allowing the task to overlap. The controller is implemented in the Python using the OpenCV, NumPy, creating and also socket communication. The speed trial 2D Unity simulation acts as the real-time plan and communicates through the three TCP sockets, which is the front camera on port at 0 rear camera on port at 0 and also vehicle control on port at 0 This setup allows us to model the key RTOS concepts such as priority the task, priority scheduling, and set inter-task communication before deploying the actual to the actual hardware.
I'm pausing and I'll talk about the simulation implementation. So we are implementing a concurrent design, which is from perceive to compute to actuate. So what does perceive means? In perceive stage, the front and rear capture tasks continuously read the latest camera frames and keep only the newest frame. So stale frame backlog is avoided and the latency stays low. In the compute stage, the processing task runs the analyze drive function in our Python code, where the vision results such as road detection, token detection, low light detection, and also event detection are fused into one prioritized driving decision, where I'll show later in the slide. And in the actuate stage, the control task sends steering and acceleration to the simulator at a fixed rate. Steering is applied as short pulses, which helps reduce oscillation and keeps the control independent from the vision jitter. So here is our task architecture. We have mainly four tasks here, which is read front camera, processing, send controls, and read back camera. So all of them are running with the same 5 millisecond period, which gives a normal 200 Hz control loop. So the difference is in the priority. The front sensing decision and the actuation path is assigned high priority because it is the most critical for keeping the car stable. The rear camera is assigned low priority because it is mainly needed for the chasing car event. So even though the task period are equal, priority helps the system serve the most safety critical control path first. We also have two helper threads for network setup, but they are not periodic and do not remain in a steady state schedule. So this is our decision logic following the perceive, compute, and actuate pipeline. In the perceive stage, the code reads the latest front and rear frames every cycle and keeps only the latest frame to avoid the stale frame backlog. Then it applies ROI, which is region of interest selection, so each detector only processes the relevant image region, for example, only in the road areas. We use HSV and BGR because HSV is more stable for separating colors, while BGR is useful for extra filtering. From there, the system builds a road mask, fits lane boundaries as smooth polynomials, and extracts tokens and event objects with size, shape, and overlap filtering. In the compute stage, each action is represented as a candidate path, and the code chooses between them to using a priority chain. The emergency edge escape is triggered by a special check when the car is already in lane 1 or lane 5 and a red token is detected in the same lane. The function immediately returns an override path. The golden lane tracking computes the center of the target lane from the fitted road boundaries and assigns a strong priority score. Police car avoidance treats the police car as a block interval and chooses the safer side of the road. The chasing car avoidance uses the rear detection to generate a lateral escape direction with lane boundary checks so the car does not steer outside the road. The red token collection during the police event treats the red tokens as targets instead of hazards and only selects them when their front priority is strong enough. Hazard avoidance measures the block regions caused by red, yellow, or grey tokens, then chooses the best remaining gap. Green token pursuit scores green tokens by closeness to the player and alignment to the center, then selects the best target if no high priority path overrides it. In the actuate stage, the chosen path is converted into steering and acceleration outputs. Steering is not continuous in the code. Instead, the control task converts the selected direction into short tap-style pulses with cooldown and confirmation logic. So this is the simulation performance data for our RTOS system, and we get an average of 58,400 from 10 sample data. So basically, we managed to get most of the events correct, but event 3 and green light token tends to not pass as often as the other events.
Hello, my name is Guan Jitong. Now I will proceed the presentation for my part, case study and comparison. Hello, my name is Guan Jitong. Now I will proceed the presentation for my part, case study and comparison. So for case study, case summary, our case study is a 2026 paper running a quantized yellow VNN detector on NVIDIA Jetson Ori Nano. It used the same perceived compute actuate pipeline as ours. A stereo camera feeds the detector. The decision stage reads obstacles and traffic lights, and command go out through RS2 like real systems such as AutoWare. It treats perception as deadline-bound real-time tasks, hitting about 98% deadline compliance. So for scheduling review, what makes it rigorous is how it guarantees timing instead of guessing frame rates. They measure execution time and apply rate monotonic and EDF test the same RS2 callback timing Cassini et al. Analyze. And for comparative analysis, so this is the benchmarking between case study versus speed trials 2D. From attribute platform perception, middleware, scheduling, timing metric, and guarantees. So you can take a look on this table to see their difference.
I'm Yu Chun. I will talk about the redesign proposal and conclusion. So to transition from a simulation to a physical vehicle, we must prioritize stability and height speeds. So first we propose dropping the Python GIL by moving to a Compass COC++ Autos model for the true concurrency. Second, we will decouple task rates running with critical actuation at 1 to 2 kHz and heavier precision at above 100 Hz. So to prevent bottlenecks, we replace the coarse mutexes with log-free buffering and add predictive control to compensate for sensing delays. So the second one is the sensor stack scaling. So scaling to a fused camera, LiDAR, and radar setup drastically decrease the compute load. So to manage this, we are making 4 architecture, which are assigning dedicated acquisition tasks for each sensor, using the DMA-backed ISRs to limit the interrupt latency, offloading heavy perception tasks to an edge GPU, and also implementing a robust sensor fusion task using the timestamp buffers. So we cannot rely on the manual operation to make sure safety. So we must validate it rigorously. So this requires tradings which profiling worst case execution time to ensure our mathematical scheduling bounds are met. So second is the hardware in the loop testing to expose the true hardware latencies and jitter. Third is the safety threshold by strengthening the system until the deadline slip, marking exactly when we must switch to a field safe mode. So for the conclusion and key insights, so building our speed trials 2D controller proves the direct link between the scheduling and responsiveness. So running concurrently at 200 Hz. However, regardless schedulability reasoning exposes the real bottlenecks caused by the Python GIL and cause mutexes. So our biggest takeaway is that our project shows how a simulation controller can be used as a stepping stone toward a more rigorous physical real-time system. That's all from me. Thank you.